An investor is looking to take $12,000 and in 15 years have it grow to $45,000. At what interest rate, compounded continuously, will the investor need to achieve their goal? So they're looking to make an investment, and they basically say, okay, I've got to go and find the right interest rate. What's the investment that will give me what I need? What's that interest rate that I need? Now, when it comes to these types of questions, you sort of need to know how much are we compounding. There's two big categories. There's compounded sort of over in discrete time periods, and there's compounded all the time, which is compounded continuously. So we're going to do that one. We'll come back to this part later, the quarterly one. So the compounded continuously model is the one that says the amount in the future A is your present value, e to the RT. So we can sit down and say, all right, if nothing else, start reading the problem and see how many things you can figure out we already know. And we'll start with numbers. Here's a number, 12,000. Where does that fit into the formula? It's P. It's how much I have right now. Like, great. This is my present amount. Okay, and we see, aha, here's another number, 15. Where does that fit in? T. That's our time. And of course, pay attention to how they're measuring time. Sometimes they'll say years or months or weeks, but this time it's years, and everything for us is cued off of years. So T is 15. And have it grow to $45,000. Okay, what's the 45,000? It's A. That's your future amount. All right, so the good news is we know many things. But we don't know all things. And what is it we're looking for? Well, we're looking for the interest rate, so we're trying to solve for R. So good news is we basically have accounted for everything. We said, look, there's one thing we don't know, and that's the thing we're solving for. Everything else we know. So life is good. So it's a matter of saying, all right, we have the following situation. 45,000 is equal to 12,000 e to the 15r. And we need to get r by itself. Now, how to do it? So, we'll do a little bit of a digression. If we need to pull something from the exponent, or upstairs, if you like, how do we do it? Now, you basically say, you're trying to solve for something. Is it downstairs? Is it upstairs? This is upstairs. There's a tool. Now, when something is upstairs, what's happening, that's in the exponent. And so it's behaving like an exponential type function. And what you want to do is say, well, I need something that undoes an exponential function. So, what we have is logarithms. So logarithms are designed to undo exponential functions. By default, I use natural log. Any log will work. Now, why do we use logarithms? Well, logarithms have some really great properties. So one in particular, the one that we're going to use most often, is if I have log of a, where a is just a number, raised to a power b, so I have something in the upstairs, then this is equivalent to b times natural log of a. So this is the key formula for us when it comes to natural logs. It has this ability to pull things out of the exponent. And so now it comes down, and so instead of having to think of it in terms of exponentiation, we can think of it in terms of multiplication. And that's something we can handle. Now, that's not the only cool property of logs, but that's the one that we're going to key off of. Some other cool properties of logs that are good to know. If I have multiplication on the inside, so log of A times B, what does that become? Do you remember? Multiplication becomes addition. Log A plus log B. If I have division, log A over B, division becomes subtraction. And if I have log of A plus B, that becomes a headache. Why? Because logs aren't compatible with addition. Logs are built for multiplication. So if you have a plus sign in the log, you're like, dang it, gah. Now, you don't have to use such aggressive language as dang it, but you might feel that way. So just remember, you're looking for exponentiation, so something upstairs, or multiplication, division. You do not want to have addition. If you have addition, something bad has happened. All right, so that's our goal. Now, to get there, to help us get there, I like to get the part where I have the part upstairs by itself. So I'm going to move this to the other side. And that's not so bad. We can just use division to move that across. And because we have lots of zeros, we can get rid of a lot of zeros. We can even simplify it a little bit further. 45 and 12 both have a factor of 3. So we could say that this is the same as 15 over 4. Or 3.75 if we were so inclined. All right, so we now have e to the 15r is equal to 15 over 4. Now what we're going to do is say, all right, let's pull out our log tool. Now, we have two things are equal to each other. If two things are equal to each other, then if I do an equivalent thing with those, the result is still equal. So we've done things like, add the same thing to both sides. Multiply both sides by the same thing. And in this case, what we're going to do is we're going to say, well, we're going to put both sides into the same function. And this is how we use the log function. So log of e to the 15r is log of 15/4. So what happens to our left-hand side? Log of e to the 15r. What happens? In particular, what happens with this 15r? Comes down. It's going down. Down, down, down. It's going down. To the front. Okay. Now, do we know what log of e, natural log of e is? It's 1. So this becomes 1, so it goes away. So we're almost there. We can now divide both sides by 15. Get r is 1/15 log 15 over 4. Well, that's not the easiest thing for us to figure out, but that's okay. We have technology. All right, if we can get our technology to work. So we'll take 1 divided by 15. We're going to times that by natural log of 15 divide by 4, and we get out that r is 0.0881. And pay attention to the problems. It'll oftentimes say use 2 digits or 3 digits. Now, as a percentage, remember that if we wanted to convert this to a percentage, we have to move over 2 digits. So this is the 8.81%. So essentially, that's what we're looking for. That's our rate of return, if we're compounding continuously. Now, different question. What if it's compounded quarterly? And you might say, aha, this will be the easier question because Steve left himself a lot less space. No, Steve was very foolish and not strategic. This will probably not be the easier question, but that's okay. We'll make it work, right? So we have a formula. So our generic formula here is our future value A, our current value P, and then we have 1 plus R over M to the MT. Now the good news is the symbols that match, the A, the P, the R, the T, still are the same, right? So we don't like, oh, what's P now? Oh, no, it's the same P. But we have one new symbol, M. What's M? What does this M, either as a number, or you could say, what is it representing? What? 4. Yes. Now, here, it's keying off of this word. So M is how often per year do you compound? So you're breaking up, saying, well, I'm not compounding it all at once over a year. I'm compounding it several times. And it's like, well, how many times? So M equals 4. So if we just plug in what we have, what do we have? We have 45,000 is equal to 12,000 times 1 plus R, which we don't know. It's not 8.81. We're still solving for R over M. And then we have, R over 4, because we know M is 4. And then we have 4 times 15, because T is 15. So to the 60. I can do the same thing previously where I divide to move things across. So you get that 1 plus R over 4 to the 60th power is 15 over 4. We have the same kind of issue, just in a different way. Previously, we said, well, we got to do something to get the R out of the exponent. So we did log. Now there's a different situation happening here. R is trapped inside something raised to the power 60. So the question is, how do we undo raising something to the power 60? Can it be undone? Now, spoiler alert, do not multiply this out. That will be a bad day. Actually, it'll probably be a bad week by the time you're done, because it'll take you a long time to multiply this out. Let's think of a simpler thing. Suppose I said it was squared. If I had 1 plus R over 4 squared, what would you do?
Take the square root.
You take the square root. Now, the thing is, 60 and 2 aren't that different. They're numbers. And so you say, okay, well, what was like the square root? It's like taking it to the 1/2 power. So what you can do is say, well, I'm going to take a root, not a square root, but I'm going to take and raise it to the 1 over 60th power. Now, if I do it to both sides, I'm good to go. Because as long as I do the same thing to both sides, then I maintain the equality. And be careful here. When I say do the same thing, like I have to plug in the whole thing. I can't just like cherry pick, like, oh, I just want to do it to this one little piece. No, I got to do it to the whole thing. Now, if I have something to a power to another power, what do I do with these two powers? What's the rule? They cancel, because what happens is you multiply them together. You know, if I take x cubed to the 4th power, that's x to the 12. So if I take something to the 60, to the 1 over 60, well, 60 times 1 over 60 is 1. So now we have 1 plus r over 4 is equal to 15/4 to the 1 over 60. So we freed the r. It was trapped inside of something. And that happened in both cases, right? In here, it was trapped inside the exponential function. Here, it was trapped inside taking something to the 60th power. We're almost there. What do we need to do to solve for r?
Subtract 1 and multiply by 4.
Yeah, if we subtract 1, that gives us r over 4 is 15/4 to the 1 over 60, subtract 1. And so that says r is 4 times, and I should have put parentheses here, 15 over 4 to the 1 over 60 minus 1. And the good news is your calculator can handle this kind of computation to the 1 over 60. So what do you do? Well, if you have a calculator like this, 4 times, I'll throw in parentheses, make sure you are capturing everything. So that's why I'm very generous with parentheses. The caret means the exponent. 1 divided by 60. Then I subtract 1. I need one more parenthesis. And I get 0.08909. Or, move the decimal place over, 8.91% if you round. So if you compound quarterly, this says you need a slightly higher interest rate. Does that sort of agree with what we would expect to be true?
Where did you get the minus 1 from?
So you had a plus 1 here? And that's why we minus 1. Now the good news is that these are close. So the fact that they're so close to each other, it's like, okay, good. Should we expect the quarterly to be higher interest rate than the continuously? I mean, it says it's true, but is there a reason why we should think it's true? So what's the difference? In quarterly, we have sort of fewer opportunities for interest to grow on interest. So if you have something growing quarterly, we should expect it to grow slightly at a slower rate than if it were being compounded continuously. So if I want to end up at the same place, if the two rates were equal, continuous beats, discrete. So if I want them to actually tie at the end, the discrete has to make up for it by being slightly higher. So that's consistent. All right. Good. Well, now in the few minutes left of class, no. Plenty of time. Okay. Throw in a fun quote from Montgomery Scott. You might recognize as a character from Star Trek. Said, "The more they overthink the plumbing, the easier it is to stop up the drain." And that is to say, don't try to make things complicated if they don't need to be complicated. Keep it simple. Oftentimes, I think students struggle by trying to make things overly complicated. Try to see the easy and simple ideas. Maybe I shouldn't say the easy ideas, but the simple ideas. Being simple can be very challenging. Now, what's our goal for today? We have to finish up our section, and we actually have just one idea left, and that's annual percentage yield. And what's the idea? Well, it says, look, I'm a simple person. I like to just have a single number that somehow captures what's going on. And so maybe I'm trying to look at these investments, and I say, well, here's an investment that's compounded quarterly at a certain interest rate. Here's one that's compounded monthly. Here's one compounded continuously. I just say, well, look, come on, just boil it down to something so I can do an apples-to-apples comparison. So this is also known as the effective rate and true interest rate. And the idea is, imagine that instead of being compounded, twice a year, 4 times a year, continuously, whatever, just once per year. What's the equivalent interest rate I'd have to get if I was compounding just once a year? And so how do you find these? Well, there's formulas for these. And so the continuous one, it's take e to the r subtract 1. Now, in case you're wondering, wait, what? So here's how you should think of it. It's actually right here. This is how your investment would grow in 1 year, right? So t equals 1. P e to the r times 1. This is simple interest. P times 1 plus an interest rate. And now what happens? Well, you have your p's on both sides cancel, and then you can subtract 1 to solve for your annual percentage yield. The same thing happens for the discrete. So essentially you say, think about the interest I'd earn in 1 year, and then say, what would be my interest rate if I was just doing simple interest, just compounded once per year? All right. Well, let's try this out. And that's the idea. So we'll just jump into. Any questions on this? At least the idea. The idea is, think of it, what would I have to invest if I only got a simple interest rate to get the equivalent return? So what is the annual percentage yield, APY, for money invested at an annual rate of 5.15% compounded continuously, or at 5.2% compounded semi-annually? So one thing you can do, if you aren't great at memorizing formulas, is just think about, okay, what if I invest $1? If I invested $1 compounded continuously, how much would I have at the end of the year? So I have 1 times e to the 0.0515 times 1, right? So you have your a equals p e to the rt. So this is how much I'd have if I invested $1. And so, okay, so we pull out our calculator, and I know you're thinking like, Steve, why do you use the calculator so much? Well, we're in the part of the course where they have us use numbers that you can't do computations on top of your head. So this says, look, this is, at the end of the year, I'd have 1.052849, ... So that would be my return. Now, of course, if we were talking actual money, they'd round it to, you get a nickel. Now that's if I invested $1, compounded continuously. If I compounded at simple interest rate, what would I have? Well, I'd have 1 times my initial amount, 1 plus whatever my annual percentage yield would be. So I get 1 plus my annual percentage yield. So these two are supposed to match. So now we just say, we can do our subtraction and get annual percentage yield equals 0.052849, and move the decimal over, we'll round 0.28%. So if we compound continuously, we'd say, that's 5.15%, but you say, well, that's equivalent to saying you get a return of 5.28% if you were compounded yearly. All right. Or we could have just plugged it into the formula. The formula would have given the same thing, right? Because this is e to the r and 1 plus APY. So this is e to the r minus 1. All right, compounded semi-annually, should we? Well, let's just use the formula. Semi-annually, how many times do we get our interest? Twice. So, formula says 1 plus r over m to the m minus 1. All right, so this is how much you'd get if you invested $1 minus your actual dollar that you invested. So for us, 1 plus, move the decimal over, 0.052 over 2 to the 2 minus 1. And what does that turn out to be? Well, okay, it's 1 plus 0.052 divided by 2 squared minus 1 is 0.052676, or, moving your decimal over, 5.27%. So which one's a better deal? Which one's a better investment?
Compounding continuously.
Yeah, it's a bigger number. The bigger the number, the better the deal. Now, we might say, wait, initially the compounded continuously number was lower than the compounded semi-annually. And that's why you have to say, well, look, it's not a direct apples to apples comparison. And so what you can get by looking at this annual percentage yield, you can say, well, let's make them more comparable to each other and say, hey, which one really is giving me my better rate of return? So that's why we might want to look at this. It helps us understand, hey, don't just look at the number in front. Also take into account how often you get compounded, because that can affect your overall return. All right. So, a bank wants to offer a CD, stands for a certificate of deposit, with a monthly compounding rate that has an annual percentage yield of 8%. What annual nominal rate compounded monthly should it use? All right, lots of words here to think about. So, we see a couple of things. We see APY. We say, okay, if we see APY, hey, we know there's a formula for that. So we're going to think about our annual percentage yield. Now, we have to think about which case are we in. Are we in continuous or are we in discrete? Because there's two variations. Right, so if we were continuous, we'd use e to the r minus 1. If we're discrete, we use 1 plus r over m to the m minus 1. So which version are we in? And how do we know? Is there any clue, a word that might help guide us? We're in discrete, that's correct. What's the one that helps figure it out that we're in discrete? Monthly. Yeah, because it's going to tell you how it compounds. So this is saying it compounds monthly. Okay, so let's think about what we know. We have our basic formula, our annual percentage yield. These are not three things, this is one thing. 1 plus r over m to the m minus 1. So there's three things here. This rate, annual percentage yield, this rate, R, and then this, M. Which things do we know? Which things do we not know? We see an 8% here. What does that correspond to? Well, it's 0.08. Which one of these is 0.08? The APY, right? Because it's the APY of 8%. So we want to say, hey, our average annual percentage yield is 8%, or as correctly pointed out, 0.08. So the annual nominal rate, this is what they're saying is R. All right. What is, do we know one of these other symbols, I guess I should ask? M. What is M? And how do we know it? M is 12 because it's monthly. And what we're trying to solve for is this annual nominal rate. So it's sort of saying, hey, this is the rate we're advertising. We're advertising, it's, I don't know what the answer is going to be, 7.5% compounded monthly. And then it says, well, what's the annual percentage yield? Oh, it's 8%. So, good news is, we know most of these things. There's only one thing we don't know. That's a good scenario for us. We like that scenario. So we have 1 plus r over 12 to the 12 minus 1. All right, so how do we proceed? Okay, we'll add 1 to both sides. 1.08 is 1 plus r over 12 to the 12. And then what? Well, the problem is the r is inside this to the 12th power. So what can we do? The same thing we did before. Raise both sides to the 1 over 12. We had to wait until after we moved the 1 across. If we didn't move the 1 across first, this wouldn't work. Because powers in addition and subtraction do not work. It's the same thing with logs. You don't want to mix them. All right, so at this point, we say 1 plus r over 12 is equal to 1.08 raised to the power 1 over 12. And at this stage, we've seen things like this before. We'll subtract 1. And then we'll multiply by 12. So r is 12 times 1.08 to the 1/12 minus 1. And at this stage, well, you have to use technology. So 12 times, throw a parenthesis in there, 1.08 to the power, parenthesis 1, divide by 12, parenthesis minus 1 equals, and we get 0.0772, or if we move the decimal over, 7.72%. So that's the says, look, we have an interest rate of 7.72% compounded monthly, which is equivalent to saying that it's going to give you an annual percentage yield of 8%. Any questions? Okay. The one for continuous, what annual nominal rate, compounded monthly, has the same annual percentage yield as 6.75% compounded continuously? Now, in case you're saying, this is a very convoluted problem, it's from the book. Whoops. We have our continuous, if I can spell continuous, e to the r minus 1. We have the discrete, 1 plus r over m to the m minus 1. All right, so what annual nominal rate compounded monthly has the same annual percentage yield as 6.75% compounded continuously? So, do we need to use the e to the r minus 1, or do we need to use the 1 plus r over m to the m minus 1? And why is the answer yes? So, which one do we need? We need both. Because what are we trying to do? We're trying to compare two things. We're saying, hey, one thing is compounded monthly, one thing is compounded continuously, but I want the same annual percentage yield. Now, notice, what are we not solving for? We are not actually solving for what the annual percentage yield is. The question, we're looking for a rate. So we're not after the annual percentage yield. Now let's talk about our two investments. So there's the continuous investment, there's the monthly investment. And we say, well, for the continuous investment, our annual percentage yield, using our formula here, would be E, and we convert 6.75% to 0.0675 minus 1. So that would be the annual percentage yield for that investment. What about the monthly investment? What would that be? Well, it's 1 plus r over 12 to the 12 minus 1. And this r, this is the r we're trying to solve for. Now, the point here, these have to be the same. I can compute my annual percentage yield in two scenarios, and it says, well, we have the same annual percentage yield, so what are we going to do with these two expressions? They're equal. They're the same. So we have e to the 0.0675 minus 1, 1 plus r over 12 to the 12 minus 1. All right. And now we're back into familiar territory. What can we do? You can add 1 to both sides. Okay, that gets rid of the minus 1s.
Take the log, natural log.
Well, we don't need to take natural log because what we're solving for is r. That's not upstairs. So you use natural log when it's what you're solving for is upstairs. R is inside a power. So we don't need to use natural log, but what would we use? Yeah, we'd take a root to get rid of the 12th power. So e to the 0.0675 to the 1/12 is equal to 1 plus r over 12 to the 12 to the 1/12. But the point here is that this becomes 1 plus r over 12. All right, well, from here, we subtract 1. And oftentimes, people will see that you can put many of these pieces together. But we're going through it slowly just to emphasize. So r is 12 times e to the 0.0675 to the power of 1/12 minus 1. All right. Now, before we compute this, we should note it should not be too far away from 6.75. So if we get an answer that says, oh, it's like 6,000%, we did something wrong. But let's hope that we are close, because that's usually a sign we did something right. And I like to think we can do things correctly. I'm a big believer in that. Okay, so we'll take e to the 0.0675, and then we're going to take that to the power 1/12, and then we'll subtract 1, and hopefully if I counted my parentheses right, we get 0.0676. Move this over 2 digits, 6.76%. And you're like, aha! So, not that far off. But that's okay. We kind of knew it was going to be close. Compounding monthly isn't too bad. And that's the idea. All right, looking at the time, I think we probably should just stop here. So, thank you. We'll pick up again next week. And next week is fun, because next week we're like, hey, let's not just do it once, but let's do it over and over and over and over and over and over again. So that's next week. So, all right.